So in the last video of section 5.3 on annuities, we developed the formula 1 plus x squared plus x cubed, say plus up to x to the n minus 1, where n is a number that you choose. We found that formula was one that these numbers added up to 1 minus x to the n over 1 minus x. Okay. The question is now, and this was our main formula star, we now want to see how to, in this video, use the formula star in an ordinary annuity problem. So what I need to first set up is the ordinary annuity problem, and to do that I will use a timeline. So here is now, for example, and maybe here in the future is, say, maybe 6 months time, and we've got this time split into monthly periods. So here's maybe 1 month, 2 months, 3 months, 4 months, and then maybe 5 months and 6 months. So what happens at each month? What happens at each month is that a deposit is made. Let's say you've made a deposit of P dollars. P dollars deposited at the end of the month. Okay, and this process continues on. At the end of every month, you put P dollars into the bank. This P could be $200 or $100. The point to note here is that you're putting P dollars in at the every month. And so notice that we have 6 months, and we made 1, 2, 3, 4, 5, 6 deposits. Okay, so a little bit of notation. Let's let A be the amount, A subscript 0 be the initial amount of money that you have in this particular account, okay? And we're going to assume here that we're starting with $0. So we're just making an assumption here, as this is a good assumption to make. We can, of course, modify these formulas when there's not $0 to start with. But let's say that you're starting with $0 in this account. The next feature, so we have a feature here that characterizes what it means to be an ordinary annuity. What makes it an ordinary annuity is that you are making the same payment or deposit in this problem at a regular time interval. That in this problem being every month. Okay. So that's what the same payment deposited on a regular time frame is what makes this an annuity problem. What makes it an ordinary problem is that your deposits made at the end of the time period in this question. The time period in this question is a monthly, each month. Okay, so the ordinary part here is given by the end, and the annuity part is same payments or deposits made on a regular time interval. So that's why this is an ordinary annuity problem. And if you were to continue on with this problem, you could then ask yourself that on each time period, money is going to grow by I%, let's say I% interest each month. So I is a percentage, and it's the growth rate of your money on a monthly basis. Okay, so we have our money growing at growth rate on a monthly basis, and we're going to assume that simple interest is in effect on each time period. So the amount then that you would have at the end of 1 month would be the $0 you started with. That earned I% interest, right? And then you made a deposit of P dollars. So the amount that you have at the end of the first month is just P dollars. The amount that you have in account at the second month, so here we are, we have P dollars at the end of the first month. The amount that you have at the end of the second month is the P dollars that you had at the end of month one, and that is what earns the I% interest, and then you make a deposit of P dollars. And since A1 was equal to P, you'll put in P for A1. A1 was equal to P. We can see that right here. And then you get 1 plus I plus P dollars. And if you factor out the P, you will get P times 1 plus I. Okay. Now, if you continue on to the third month, right? The third month, your money grows. Here we have, here we were at the end of the second month. We had P times 1 plus I dollars. 1 plus I dollars in the account. The amount at the end of the third month is the amount that you had at the second month. That accrues interest, and then you make your deposit of P dollars. But we just showed up here that A2 was equal to this quantity, P times 1 plus the quantity 1 plus I. So we'll make that substitution for A2 right here. Okay, and I will put P times 1 plus the quantity 1 plus I. Okay, this is A2. I need to multiply that by 1 plus I, that is this quantity. And then I need to add on my P dollars. Well, if you factor out the P again in this problem, we're going to factor. You'll factor out the P and then distribute. Oh, you'll have one. You factor the P out of this whole expression, and factor P out of the P will leave a 1. You factor the P out of this quantity, and you'll get 1 times 1 plus I times 1 plus I. Distribute the 1 plus I, distribute the 1 plus I, and you will get 1 plus I plus 1 plus I squared. And that's the amount that you have at the end of the third month. I think you can hopefully maybe see a pattern here that this is a 3, and we've extended this up to the second power. When the number was a 2, we extended these pluses up to the first power. So I think you can see here that maybe A4, the amount that you have at the end of the fourth month, will be your third month. That will accrue interest. That is this line. Then you will add on your P dollars. And if you make this substitution for A3 and do the factoring, this step, and the distributing step, you will see that you get P times 1 plus I to the first, 1 plus I to the second, 1 plus I to the third. And therefore, if you continued on with this process, there would be the amount after the fifth month would be P times 1 plus I, 1 plus I squared, 1 plus I cubed, 1 plus I to the fourth. So notice here, 4 you go up to the third power, 5 go to the fourth power, and then you can get to the sixth, and you will get P times 1 plus I, 1 plus I squared. I'll skip some steps here, and we will go up to 1 plus I to the fifth power. Now, of course, your job is to then be able to compute these quantities. So, for example, here, if I use this specific example, that maybe I wanted the amount after 6 months, and you were putting in deposits P of say $100 every time, and your interest rate was say 1% every month. This is a 1% per month. So that's the amount of interest you earn over this the time period in question, which is a month. And then I think you can see the amount that you'll have after 6 months is going to be $100 times 1 plus 1.01 to the first, 1.01 to the second, 1.01 to the third. Keep going until you get to 1.01 to the fifth power. And this should look a lot like the formula we had a second ago. You should compare this to the main mathy formula, which was 100. And this part underlined looks an awful lot like 1 plus x squared plus continuing on up to x to the n minus 1. And then we remember that that should be 100, 1 minus x to the n over 1 minus x. That's the main mathy formula. It's only up to you now to determine what are the variables in question. So I think you can see here that x is equal to 1.01. Okay, and our n value, we are going up to we want n minus 1. You want n minus 1 to equal 5, which implies that n has to be 6. So this tells you that the amount after the 6th month is going to be $100 multiplied by 1 minus 1.01 to the 6th power over 1 minus 1.01. Okay, and that would give you your dollar amount. Okay. If you look a little deeper into this problem, we'll look a little bit deeper. What color should we use for that? How about blue? Okay, if you look deeper, okay, into this formula, the amount after 6 months, and we start looking for a pattern here. Okay, you'll maybe recognize that the 0.01%, okay, here's your P dollars that you are depositing every time. 1.01 is the same thing as 1 plus the I amount. I is the 1%. Okay, and 6 months is how long we were going for. So here is your monthly interest rate. Okay, and here 6 is the total months that you wanted the money to grow for. And we also have on the bottom 1 minus 1 plus I. Now that simplifies to 100. 1 minus 1 plus I to the 6th power. 1 minus and a 1 plus I just simply becomes negative I. Okay. And we can see here that if you, since they both have a minus sign in them, here I'll just do this 100. Factor out a minus of the top, and that would give you 1 plus I to the 6th power minus 1 divided by negative I. The minus 1s will cancel and leave you with a very important formula that the amount that you have after 6 months is the P dollars that you were depositing every month. Okay, 1 plus I to the 6th power minus 1 over the quantity I. Okay. Now this will extend that the amount that you're going to have after n months, n total months, is going to be your P dollars, 1 plus I to the total number of months n over subtract 1 and then divide by your interest rate I. And this is the other main formula from section 5.3 for ordinary annuities formula, the amount that you have in the future. This is the future value formula for the ordinary annuities problem. Okay. One more step here. So we have the amount after n months. After is p dollars 1 plus I to the n minus 1 over I. Okay. Your book gives us a formula. They call this the amount that you have after a total number of time periods. They call this the formula S. And instead of p dollars being deposited, they call that the quantity R. 1 plus I to the n minus 1 over I. Hopefully the formulas don't give you too much bother. They're just changing the letters. But it's R is the amount. R is the amount deposited at the end of whatever time period is in question. I is the interest rate on the time period in question. If it's a monthly time period, you need an interest rate per month. If it's a yearly, you're making deposits every year, you need the interest rate over that year. So that's the quantity I. And S is the amount in the future, N time periods later. Okay, so that's the main formula for section 5.3 for ordinary annuities. There are other types of annuities, and we will look at those later in another video and in class.